Hi, I'm Natalie, and I'm going to be talking about recent work on the Pauli spectrum of QAC0 with my wonderful collaborators, Shivam, Francisca, and Henry. So first, I'm going to break down the title for you. QAC0 is a quantum circuit class. The Pauli spectrum is a mathematical tool that we're going to be using. And finally, we're going to need some perspective to combine the two. And in fact, this perspective is, one of the main contributions of this work, defining the right object that we're going to Pauli analyze to get sort of useful statements. So, and kind of like once we have the right object to analyze, some nice results kind of fall out of that. So to outline what we're going to talk about, we're first going to motivate the study of QAC0 circuits. We're going to learn about the Pauli spectrum and finally connect the two. So connecting Pauli spectrum to quantum circuit complexity. So quantum circuit complexity, we're specifically going to be looking at the complexity of computing Boolean functions. And so for quantum circuit, I've drawn here the depth is the number of layers, or time, size is the number of gates. And when we talk about circuit lower bounds, we're talking about lower bounding these two measures of complexity. And since this talk is so short, I'm going to be prioritizing, kind of highlighting for you all the like main ideas and observations that shape this work. And I'm going to spend relatively much less time on motivation, but hopefully since you're watching this YouTube video, you already care about quantum circuit complexity, and I don't need to explain to you why it's so interesting. So the existing techniques we have for analyzing quantum circuits are kind of largely, most of them really boil down to what's called a light cone argument. And this argument is the simple observation that if you were to measure one output qubit of a quantum circuit, that the probability distribution of this measurement is going to only depend on the inputs in its backwards light cone, which I've drawn here. And in the case where your circuit only has gates that are acting on 2 qubits and the depth is d, the light cone size is at most 2 to the d. So when you have a quantum circuit with constant size gates and sublogarithmic depth, this imposes a pretty severe structural limitation. And so, that one output qubit can't even depend on all the inputs. And so, we might hope to have more techniques besides this one. And that's one of the main motivators for this line of work, is trying to go beyond light cones. So on one hand, we have these constant depth circuits, very restricted by light cones. But, once your circuit has logarithmic depth, now one particular output qubit can depend on all the inputs, and the light cone in and of itself isn't restrictive at all. And in fact, we have no known lower bounds against these logarithmic depth quantum circuits. And actually, there's a pretty strong barrier against proving such lower bounds. So these log depth quantum circuits can simulate log depth classical circuits, for which it's kind of a long-standing open question of trying to prove lower bounds against those. And so getting a new lower bound would be like a really big breakthrough classical result. And so, you might hope that, as a first step, there's something intermediate that doesn't have such strong barriers against proving lower bounds. And this is where QAC0 enters the picture. So, or where QAC0 is a nice object to look at. So before I tell you about QAC0, I'm going to tell you about AC. Remove the Q, remove the 0. And now we have classical AC circuits. So these are probably, the first circuit that everyone learns about. This is where it's a classical circuit. You have and, or, and not gates, and you're allowed unbounded fan in. So here we have time still going left to right, and the depth is the number of layers, size is the number of gates. And when we say AC0, this means constant depth, and unless otherwise stated, we're assuming polynomial size. And in fact, we have lower bounds for AC0 that AC0 doesn't. This light cone argument also fails because you have unbounded fan in, and so. Famously, in 1986, Hadstad showed that parity cannot be computed by AC0. So, this is kind of like a nice place to look, trying to generalize this into a quantum argument. So now we have QAC0. So this is the quantum analog of AC0, where we're allowed arbitrary single qubit gates and many qubit CZ gates, which can be interpreted as a quantum AND gate, which I've defined here on the right. And this class of circuits was introduced in 1999 by Moore to try to come up with a quantum analog of AC. Again, QAC0, we're referring to constant depth, polynomial size. So why should you care about QAC0? As I kind of hinted to before, they are in fact intermediate between constant depth and logarithmic depth quantum circuits. So, you know, we're in the circuit model where the light cone argument breaks down. But actually, this is really in a nice frontier of quantum circuit complexity, because we don't know whether or not QAC0 can simulate all polynomial sized quantum circuits, but there's no known barriers for proving otherwise. Whereas, for these log depth quantum circuits, there's a pretty strong barrier against being able to prove that, prove a lower bound against them, but we don't know of any barriers like that for QAC0. So they're kind of like the most approachable circuit class to start with. And actually, like, without even going all the way to logarithmic depth quantum circuits, but if we just reach a little bit farther, another class between QAC0 and log depth, we look at, there's some class called QAC0 with fan out, which is allowed a little bit more power than QAC0. And even proving lower bounds against QAC0 with fan out would give breakthrough classical lower bounds. And so it really seems like QAC0 is at this nice sweet spot where, existing techniques break down, but so we would need new techniques, but there's no like obvious roadblocks against this. And finally, I'll note that there's some rising interest in devices that can implement many qubit operations. And so I guess some experimentalists are also somehow interested in QAC0. And one of the big open questions surrounding this quantum circuit class is parity computable by QAC0? So, recall that, famously Hadstad showed that parity is not computable by AC0. Can we extend this to QAC0? And surprisingly, to me at least, if QAC0 can compute parity, this is really powerful. So if you can compute parity, then you can also compute majority and threshold and so on. And even like the bread and butter of our quantum algorithms class, phase estimation and quantum Fourier transform. And in the classical world, showing parity is not AC0, and the techniques that were developed along the way paved the way for many substantial classical results like listed here and more. And so, maybe we can have some wishful thinking and say like, okay, well, if we're going to need new techniques to show that parity is not in QAC0, maybe we can also have such big influence. And so we conjecture, other people conjecture too, parity is not in QAC0, and there's been some modest progress in this direction. And, like I'll note that like some of these results are, even, showing lower bounds against just if QAC0 is only depth 2. And like even these arguments are like really subtle and not straightforward. And so it's interesting that like, there's somehow a lot going on even in depth 2. And we add another row to this, and so our result shows a lower bound showing that QAC0 cannot compute parity, even in the average case, but we have this restriction that you can't have too many auxiliary qubits, at most like n to the 1 over d. And this is these rows are kind of like pairwise. Some of them are incomparable, but the general trend is like, okay, we're getting slightly better at gaining evidence that parity is not computable by QAC0. So, okay, so our goal is to develop techniques for quantum circuit lower bounds, and the route we're going to take is called is what we call Pauli analysis. So now I'm going to kind of try to walk you through this technique. So it's for those of you familiar with Fourier analysis of Boolean functions, we're trying to develop a quantum analog that's equally as useful for proving quantum circuit lower bounds. So the Fourier spectrum of Boolean functions, we have this nice property that any Boolean function can be written as a multilinear polynomial, where the monomials here are just the product of some of the inputs. And the coefficients f hat are referred to as Fourier coefficients. So the degree of a particular term is going to be the size of the subset, and the Fourier weight of degree k is going to be the sum of squares of all the degree k coefficients. And for example, parity is just going to be the product of all the inputs, because the inputs are in the plus minus one basis. And so all of its Fourier mass is going to be at level n, or degree n. So it looks like this point function. And, famously back in 1993, Lionel Mansour and Nissan showed that any function computed by an AC0 circuit has this like weight function decays exponentially in k. So you get something that looks like this. And this has some really nice implications that kind of fall out of it without too much more work. One is a quasi-polynomial time learning algorithm for AC0. And this follows from just noticing that most of the weight is concentrated below level that's like Pauli log n, and you only need to learn low degree coefficients to get a good approximation of this function, of which they're a quasi-polynomial number. And the second is circuit lower bound. So again, remember the parity function has all of its Fourier mass at level n. And so, at least in the Fourier basis, these two functions are really uncorrelated. And this, transfers over into a correlation bound. The probability that some AC0 function is computing parity is small for a randomly chosen input, or is like close to 1/2. Okay, so this is really, really cool. And, hopefully we get something like this maybe for quantum circuits. And kind of one of the main takeaways from that result is that they relate the degree of a function to its computational complexity. And, our goal is to find some notion of degree for quantum processes that we can relate to the quantum computational complexity. And, finding this right definition of degree is somewhat the puzzling part. So here's our first attempt. We're going to do Pauli analysis of unitaries. What is this? This is something proposed back in 2010 by Montanaro and Osborne, where you can write any unitary, n-qubit unitary, as a linear combination of n-qubit Pauli operators. I mean, this is true for any square matrix. And we're going to call the degree of one of these terms, the degree of a particular Pauli is going to be the number of non-identity terms in the Pauli string. And so you might hope that if your unitary U has large degree, that it requires a large quantum circuit. But unfortunately, this is not the case. And there's a really simple counterexample where you take the quantum circuit where you just apply a Pauli Z to every single qubit in parallel. So this has depth 1, but the unitary is just Z tensored n times. And so this has full degree n. This is like a contradiction, but this is kind of, not satisfying, because if you only care about this last output bit, this morally has degree 1, right? The last output bit only depends on one input, and the other Z gates aren't even affecting you at all. You might as well remove them. And so there's kind of this mismatch between this Pauli analysis of unitaries and Boolean functions, where a unitary has n inputs and outputs, whereas a Boolean function has n inputs and 1 output. And we really don't care about the remaining outputs of this unitary. So what we do is we don't restrict ourselves to unitaries, we look at channels, and we're just going to throw away these extraneous qubits that we actually don't care about when we're at the end of the day, we care about whether or not the circuit can compute a Boolean function. So we just throw out the rest. And so mathematically, this looks like the channel, you apply your circuit to your input state, and then you trace out this jump register. And, kind of like the new insight in our paper versus previous works that look at Pauli analysis is that we're going to be looking at the Pauli spectrum of this n qubit to 1 qubit channel. Now, what does that mean? So what is the Pauli spectrum of a channel as we work with it? we're going to be the object that we're going to be looking at this Pauli expansion of is the Choi representation. The Choi representation is the resulting state if you were to you took n bell pairs and you sent half of them through your channel. And in our case, they're like for the representation, they're not normalized. Bell pairs, or the state's not normalized, but anyways, the Pauli weight of degree K is now just similar to in the Fourier, for Fourier analysis, it's just the sum of magnitude squared of all the Pauli coefficients of degree K. And, just as a quick note to kind of start to give you a taste of why this is a nice thing to do is that if you consider the setting where you're actually just looking at, you just have a classical function or a Boolean function, and you look at the quantum channel that's just implementing this, your quantum channel is actually just implementing this Boolean function, that the Pauli spectrum and the Fourier spectrum are actually equivalent. So this is nice. We have that the Pauli spectrum like strictly generalizes Fourier spectrum. Because, okay, so here's your channel that is just implementing the classical Boolean function, first measures in the computational basis, computes the Boolean function, outputs it. And here we have the Fourier spectrum is exactly the same as the Pauli spectrum is the same as the Fourier spectrum with this extra identity term that's required because, state has to have trace 1. And, the characters are Pauli z's rather than, just a product of the inputs. So this is a good sign that okay, we're on the right track. And, let's recall this LMN low degree concentration of AC0 result where we have this exponential decay in Fourier weight. And the takeaway from this is that AC0 functions are approximately low degree polynomials. So by this point, you're all probably wondering, are QAC0 channels also low degree polynomials? And let's look back at this example of a channel where you have your input is a computational basis state, or your input is a quantum state, and then you only have one output and you throw out the rest. Actually, this channel is in fact low degree concentrated, and our bound is like almost the same as LMNs. So yeah, yay, we do have this Pauli spectrum that decays exponentially with weight. So, we were probably all excited about this, but then maybe half of you are like, well, wait a second. When I interact with my quantum computer and I run a circuit, I usually also give it some auxiliary qubits. So here you might say, well, I want to allow my circuit to not just take the input to the problem, but also take some auxiliary register that's just always set to the all zero state. This is actually a really helpful thing to do and can give you more space to compute. Unfortunately, once you allow yourself to have auxiliary qubits, our concentration bound blows up by a factor of 2 to the A. And so, only when A is much less than n to the 1 over D do we get this exponential decay in Pauli spectrum. Yeah. So this is annoying, but we conjecture that this pesky dependence on 2 to the A is not necessary, and that the statement holds without it. Couldn't prove it, but we think it's true. And then that would be really nice. Then we kind of get this correspondence between this LMN bound against AC0 and ours would basically match it. And just as the concentration of AC0, this has some pretty nice immediate implications that fall out of it. So first is a quasi-polynomial time learning algorithm for QAC0. Just as before, most of the mass is below Pauli log n level. So we just need to learn those low degree coefficients. And secondly, circuit lower bounds. So here the parity, the channel computing parity, has all of its mass at level n and 0. The 0 is always going to be there because of this identity term. And, just as before, this gives us a nice correlation bound against parity. So now I'm going to just quickly go over the proof overview. First, we'll talk about the case where there's no auxiliary qubits. If there's, so there's two observations. There's really only two observations that we use. And the first is that if there's no large gates at all, there's no large CZ gates, then we can just use the light cone argument to see low degree. So, more rigorously, if your circuit has depth D and gates that are of size at most K to the 1 over D, then there's no weight above level K. So this is nice. And the second observation is that if we remove really large CZ gates, like the larger the CZ gate, the better. It doesn't affect the channel very much if you, choose a input uniformly at random. And so, intuitively, this is like, okay, if you have this large CZ gate of size L, right, it adds a minus sign only on the all ones computational basis state. And it just acts as the identity on all other computational basis states. So if you choose a computational basis state uniformly at random and, apply this large CZ gate to it, only with probability 1 over 2 to the L, if there's L qubits, will this have any effect on your state. So in fact, here's this, second lemma. If you have, S gates of size L, then you only incur an error that scales as like S squared times 2 to the minus L. And, the way I stated it was, okay, if you have a CZ gate that's acting on some randomly chosen input that like usually the CZ gate is not doing anything. But in fact, even if the CZ gate is in the middle of your circuit, since the circuit's all unitary, if your input is uniformly random, then in the middle of the circuit, like a uniformly random computational basis state, in the middle of your circuit, if you were to measure your state, it's also going to be a uniformly random computational basis state. And this just follows from the unitarity of your circuit. So this is nice. And combining these two lemmas, the final concentration bound follows nicely. And, okay, now what about auxiliary qubits? What breaks? The second lemma is what breaks. My argument about, once you have auxiliary qubits, you're forcing some of the inputs to be all zeros. And so you don't have that, if you remove a CZ gate, oh, well, it's only acting on a random input. Like it actually might be only acting on your auxiliary register that is somehow already fixed to 1. And so removing it might make a really big difference. And so this second lemma is what breaks. And, we couldn't figure out a way to adjust this lemma to allow for auxiliary qubits in a friendly way. So instead, to deal with auxiliary qubits, we just deal with them like at the very end. We say, okay, well, let's just assume that there's n plus a inputs. We allow the auxiliary register to just be part of the input to the channel, and we say, okay, well, this channel now has low degree concentration, but we want to fix some of the inputs now to be 0, and this corresponds to post-selecting this auxiliary register, this, because you still have, so this post-selection of the auxiliary register, which maybe for those of you who like tensor network diagrams, maybe this is helpful, but if you don't worry about it. But yeah, post-selecting this auxiliary register, incurs this 2 to the A blow up, and this just comes from the change in dimension. So, you still have the same it just comes from the change of dimension. Okay, so to summarize, we show a concentration bound against these QAC 0 circuits with few auxiliary qubits, against the Pauli spectrum. And, this kind of quickly then gives us some circuit lower bounds for, parity and majority, which I didn't mention here. And, we also construct a learning algorithm that, because of a learning algorithm for low degree quantum channels. And, since we showed that QAC 0 have low degree quantum channels, we have a learning algorithm for QAC 0. So what are some nice open directions that I think would be really exciting for any of you tuning in here to work on? One is an improved spectral concentration, obviously, so prove our conjectured concentration bound that so it doesn't depend on the auxiliary qubits. The second is developing a notion of random restriction for quantum circuits. So random restrictions in the classical circuit complexity world have been a really powerful tool that were key in Hadstad switching lemma that showed that AC0 is not in parity, or parity is not in AC0. And it'd be really nice to, I think many people want a quantum switching lemma, but kind of getting the right definition that's meaningful and useful has been puzzling. So I think that'd be really cool if anyone can come up with a nice framework for random restrictions. And finally, I'll note that having connections with this result in state synthesis would be really nice. So, for example, there's a nice equivalence between the complexity of preparing a cat state and computing parity. And it'd be interesting if there's any explicit connections between this work and these techniques that are about the complexity of computing channels with the complexity of state preparation. And, maybe just kind of somewhat out of the box, it says something about state preparation. But, I'm unaware of something like this, and I think it would be really cool. So that's all the open directions I'll mention right now. Thank you everyone for tuning into this YouTube channel and watching. Hopefully this was useful. It was quite short. But yeah, hopefully it was good. Bye-bye.